Good afternoon, everyone, and thank you again for joining us for another talk. I'm going to introduce Dr. Peter Beling. He's going to be our first presenter for this particular talk, and this is going to be revolving around ART-006, risk-based approach to cyber vulnerable assessment using static analysis. So, Peter, if you wouldn't mind, please take it away.
Good, thank you, James. Yeah, this afternoon you're going to hear from 4 members of our research team. So we'd also like to acknowledge the help of Dr. Barry Horowitz. It's also part of the team for this project, ART-006, which was sponsored jointly by R&E and by CCDC-AC, Picatinny Arsenal Armament Center. So next slide, please. So the background for this project really is the topic of static analysis. And for those who aren't familiar with static analysis, the idea in static analysis is to do an analysis of code, not by running the code, but by looking through the programming structure. And there exist various tools that are capable of doing that, looking for certain kinds of constructs within the code that could express themselves in terms of points of vulnerability for bugs or for potentially also for cybersecurity vulnerabilities. And it's the latter that we're interested in. We're interested in cybersecurity. So the notion is that the tools can discover software structures that might open up the software to attack by hackers, so they represent a kind of fertile ground for vulnerabilities, if you will. What the tools end up producing then is something that we call alerts. So these are really constitute the identification of specific lines of code or small blocks of code that are problematic and should be the candidates for modification. So next slide, please. So the DoD has a wide mandate for the use of static analysis tools in programs as software is developed. So all programs are asked to use these tools, and it turns out that there's quite a lot of tools out there on the market. So in our graphic here, we have a few of them, C++ Check and CodeSonar and others. And actually, there's a really large collection of these tools. And so the notion is that you might take your code, which for something like a DoD program might be a very substantial base of code with potentially millions of lines in it, and feed it into all of these codes, and then out comes alerts from each one of the tools, and collectively you can look at them as a big basket of alerts. All saying, hey, you should take a look at this section of your code. That's a great idea, and it's nice to have coverage from multiple tools because each tool tends to have a kind of specialization to it, being very good at detecting one kind of vulnerability, but maybe not the others. So it's good to use a collection of tools, but in the end, you're often left with tens of thousands of alerts if you're running these kinds of tools on major pieces of software. And on top of that, most of those alerts are false positives. So you have a situation where you have tens of thousands of cases where your attention is being drawn to something, and then for each one of those, you have to go in and resolve whether, in fact, a vulnerability potentially exists there, or whether the alert is a false positive. The tool is just being a little bit too sensitive. So all of that has to be done by a skilled analyst, and in the event that a vulnerability is judged to be a true positive, then there has to be an active effort to fix the problem. So all of this kind of comes together to form an enormous set of productivity issues. If we're using these tools on big programs, how do we deal with the productivity issues? An analyst might be only able to resolve 6 or 10 alerts in an hour's time, and if you have tens of thousands of alerts, that adds up to quite a lot of time. So next slide, please. So So one of the things that one can think about doing has already been done by CCDC and AC and the Army in conjunction with the Software Engineering Institute. And that's to take the collection of alerts and begin to do things with them. So for example, one could say, well, I'm going to judge an alert to be more likely to be a true positive if a larger number of tools have also flagged that section of code. Okay, so kind of do a voting scheme. Or on top of that, you could begin to use various kinds of supervised learning, machine learning techniques to begin to predict whether a given alert is a false positive or true positive based off kind of what you've seen before in terms of the quality of the individual tools or how they end up working together. And so there has been a base done along these lines. It's something called SCALE, Source Code Analysis Lab, put out by a Software Engineering Institute. And there's a particular version for CCDCAC that has some refinements along the lines of what I just mentioned. Next slide, please. There we go. So what we're out to do is starting from the base of SCALE, is to think about adding some new elements to the mix of filtering alerts to improve productivity. And we're going to introduce two principal kinds of alerts. If you could go to the next slide. And they're shown shown at the top of the SCALE box there. We have AI-based alert prioritization techniques and mission aware. And so our notion is that we're going to develop a risk prioritization, so to tie the alerts to what we care about most in terms of system risk and consequence of potential cyber attacks. That's the mission aware side. And then introduce some novel techniques on the AI side that supplement what's already in SCALE. So those are our two principal contributions in this project. And we'll talk about each one of them in turn. Next slide, please. So to start with the mission aware side, let's go to the next slide, if you would. The problem that we can think about in this context is if we knew what consequences we really cared about for a system, and if we had that in mind from the beginning, we've done a risk analysis, then the question would be, how would we tie the results of that risk analysis to the alerts generated by these static analysis software packages? So if we know that, for example, we're really concerned with fire control in a given weapon system, and we want to make sure that fire is never engaged unless an operator has really pushed the button, and that's a kind of outcome that we want to make sure is always the case. Then the question would be, how does that kind of notion, a priority of system function and a kind of high-level expression of risk and consequence, how does that end up relating to individual pieces of code? So that's what we're kind of struggling with in our first aspect of the research project. Now we have a lot to base things off of. We have just on the risk analysis side, the results of several research projects, WRT 1013, ART 004, and many others that were spoken about earlier in the day in the trust session. So I'm not going to cover the details of those methods, but I'll say that we have a lot of structured elicitation process and way of converting that process into systems models that will allow us to form a risk analysis from the beginning. And then we still faced with the question of how to relate that risk analysis to the individual code elements. And for that task, we turned to something called dynamic system testing. So dynamic system testing is done for every system at one point or another to begin to test for things like safety and operator errors, out of spec situations, and so on. And these tests provide a basis for relating test outcomes to compiler-based software testing, so we can understand the relationship between a given test that's performed and the software in terms of what elements of the software are engaged during the test. Let's go to the next slide, please. So what our hypothesis is that we can use dynamic testing in the context of cyber, because the principal consequences for loss, things associated with safety, scenarios where principal mission functions are not performed properly, and all those kinds of bad outcomes have already been tested for using dynamic testing. And so we can understand, to the extent that we can understand the cyber risks that we're worried about, we can relate those to risks that occur in other elements of the system, and then use the compiler-based software tracing to make a connection between our cyber risks and the software. So we're able to do that now, and we also have a kind of second part of that hypothesis, which says that as time goes on, that's going to be an easier and easier thing to do, as there's more and more recognition of cyber attacks as something that need to be tested for dynamically as well. Let's go to the next slide. So at this point, to give some of the details of what we've done and to take us into our particular methods, I'd like to turn it over to Mr. Tim Sherburne, and he will describe our processes. Thank you, Tim.
Thanks, Peter. So, like Peter said, this mission-aware concept has been presented, different aspects of it in a couple different presentations earlier today. So again, for the static analysis, we're not going to go into detail of the process, but just want to point out that doing this hazard analysis is a key part of identifying what the key mission concerns are for the software that's being analyzed with static analysis. And like we mentioned in some of the other presentations, there's also a methodology that goes along with this mission-aware meta model that has these multiple teams. And key here, kind of for this part of this project, this operational risk assessment. You know, what is the important operations for the mission that this software is involved in. So, and again, it's this STPA process out of MIT that we're leveraging. So it's a methodical approach, a methodical hazard analysis technique, you know, to identify what the key losses and priorities for those losses, system hazardous states. So again, it's using this process on you know, the system, the software of interest. So just a brief background, you know, for people maybe didn't see this stuff, but so using this mission-aware concept, we developed this methodology for applying it to static analysis. So this first step of this methodology is, you know, using CSRM to do this consequence analysis. And then the second step, as Peter was mentioning about, this is going to involve tracing, dynamic tracing of the software based on important system or anomaly test cases. And those were the test cases we're interested in are those that are related to the primary important missions of the system. So once we identify those, then there's kind of two paths, you know, doing the static analysis of the code with multiple tools, and then based on these test cases identified, building the software with code tracing enabled, and then run the test cases, collecting the code traces for each test case, and then finally bringing the static analysis results together with this dynamic code tracing to provide a mechanism of filtering and viewing the static analysis alerts with this mission priority view. So that's the methodology, and then we used ArduPilot as an open source autopilot as a case study for this methodology. So we did static analysis using Swamp as a open source cloud environment for running static analysis tools, and then we used the ArduPilot was built with the GCC compiler, which has tracing mechanisms that can be enabled as you run the tests, and then brought them together for this mission-aware prioritization. So I just have one slide kind of giving a little more detail about each of these steps here. So first of all, just a little detail about the ArduPilot itself. As I mentioned, it's an open source autopilot package, and it supports several different vehicle modes, and where there's a large set of shared libraries that are used across multiple vehicle modes. So we focused on the helicopter mode, and using the shared libraries. And just to give you an idea of the size of the software, it was about 217,000 lines of code, C and C++ code. Another nice mechanism that was provided with the ArduPilot is a software in the loop build, so that we could run the ArduPilot in a simulated mode just on a Linux workstation. We didn't have to have specific UAV hardware. So there was a ready built environment that we could leverage. And within that software in the loop environment, there is also an auto test suite that was provided, and mainly there for kind of a regression test of the ArduPilot as features are added. And so it's a Python-based kind of scripting environment that you can put a UAV through the motions of flying different routes and monitoring the behavior. Here, this slide is just a view of the static analysis tools that we used. There was a couple open source tools and a couple commercial tools that we were able to access via this Swamp environment. And here, this is just a view of the raw alert counts that were produced by each tool. So for the ArduPilot, the software in the loop build, it was about 1,300 alerts that were found. For the testing environment here, they're based on this auto test environment. We picked 4 kind of interesting test cases here and kind of correlated them to these types of tests, safety or component failure tests or out of spec tests. And for each of these test cases, we built the ArduPilot with the code tracing enabled. So the idea of the code tracing, it tells you exactly the functions that were called, the lines of code that were executed. And it even has, we didn't really leverage this, but it's accounts of how many times was this function or how many times was this line of code executed. So for each of these tests, here are the counts of the functions that were executed, how many of lines of code were executed for each of these tests. We also looked at, combining, was there some sets of code that was common across 2 or 3 or all 4 test cases. So combining these together, then what we have here is on the left here is the static analysis, the raw results. And then now of those 439 results for tool A, how many of those alerts were found in code that was executed by at least one of the priority test cases. And for this example here was like 91 of those total alerts. So here you can see the numbers of the attenuated set of alerts that are important based on the fact that they were executed as part of those priority test cases. So we found really encouraging results of, about 75% of the alerts could be filtered out just as part, they were in code that were not part of these priority test cases. This chart's a little bit of an eye chart here, but as Peter mentioned, we also did some work to integrate this environment with this SEI scale tool. We built some importers so that we could import the static analysis results from this swamp tool and also the outputs of the code. So you can navigate from a specific alert to the line of code. So we added here a new column for sorting on the mission priority. Just show that real quick for the mission. And so for example, this alert, if I click on it, so this jumps to this file, line 110, shows that alert. And we can see we also enhanced the header for the code, the HTML code view, to show which test cases this code file is associated with. So you can navigate kind of both ways, from a code file to the alerts that are important, or from a particular alert, you can see, all the code files that were executed as part of that test case. So with that, I'll turn it over to Davis, and he'll take us through the next part of the machine learning for alert prioritization.
Yes, thank you. Next slide, please. So we wanted to take a quick step back and just reconfigure the problem as a whole. And as Peter said, the main problem with static analysis alerts is that addressing all of them from the static analysis tools is expensive and time consuming. And as mentioned, this is exacerbated by the rate of false positive alerts. That is, alerts that say they're an issue, but in reality, there is none. So we wanted to develop a technique to help an organization effectively address the set of alerts and improve productivity overall. So we came up with a high-level framework we call the CAP methodology, which stands for the 3 phases, which are collect, assess, and prioritize. And ultimately, the objective is to prioritize static analysis alerts so that you get the most value in the shortest amount of time. And there are several ways to accomplish this. So as Tim just discussed in the RSVM methodology, we just filter out alerts that don't run in our test cases, and that's one way to do this problem. But there are a lot of tools in the toolbox, if you want to say that. So there are many ways to do this, and we'll show you an example on the next slide of a different approach to get the same result. So we run through another example, again, using the ArduPilot code base. And in this case, instead of doing code trace, we used a bunch of different methodologies, including topic modeling, simulation for resolution times and classification, and optimization techniques. And we'll go into a little more detail on each of these steps and what they looked like in our example on the next slide. So in the collect phase, we used topic modeling. And if you're unfamiliar, topic modeling is a machine learning technique to classify text based on the latent themes within the text. And in our topic model, we had 10 topics that we ranked 1 through 10 in terms of relative importance. So we ran a topic model on the ArduPilot code base, found 10 topics, and we said topic 1, the most important, was navigation control. So modules that change the pitch of an airplane, for example, fell into this parameter. And then the least important, we said, were the SIDL modules, which are the software simulation of ArduPilot. So an alert that occurs in topic 1, we would give more weight than one that occurs in topic 9. And we deprecated the value for each static analysis alert added if it was in a lower priority topic. So once we collected this data, we went to assess. And for assess, we used a couple of simulations. So first we simulated a classifier to assign a true positive likelihood to each alert. And this was based on existing research regarding classifiers for static analysis alert true positive classification. And we just used simulation, assigned one to each alert. And then we also simulated 2 times to resolve. 1 time to resolve for if the alert was a true positive, and that would take a little longer because you actually have to resolve it. And then a false positive time to resolve for the time it takes to identify how if an alert is in fact a false positive result. And again, this was derived from research and from known distributions. And finally, in prioritize, we used knapsack optimization to get as much value as we could given limited time resources. So if you look at the image on the right, you see the orange line, which is the CAT methodology, outperforms the base methodology in the blue line. And in this case, the base methodology would just be addressing static analysis alerts based on their priority provided by the static analysis tools. And as you can see, the CAT methodology outperformed the base methodology pretty rapidly. And this is mostly due to the fact that you have a lot more context, time to resolve, and relative value based on its importance to the code. However, we know we made a lot of assumptions, so we wanted to test these assumptions. And we can see in the next slide, one of our key assumptions was the true positive classification. And what we noticed here is that compared to the other assumptions, the true positive classifier had an outsized impact on CAP performance. So if you look at the graph on the right, you see as you move right and down, the orange line gets closer to the blue line. This represents a loss in confidence of your true positive classifier. So the less confident you are in your classifier, the less value you get out of the CAP methodology in this particular implementation. So given that, it's important to develop robust alert classification models so that we can maximize the impact of using the CAP methodology. And I will pass it on to Stephen, who will go into detail about that.
All right, thank you, Davis. Yes, as Davis has said, we've developed this CAP methodology that's highly dependent upon the ability to predict the true positive and false positive rate of some type of prediction algorithm. So next slide. Yep. So these true positive and false positive labels are often used to triage alerts and prioritize them. And machine learning has been used to try to predict these labels. There's been work done at SEI that just uses a binary classifier to predict the label. CNNs have also been used, and studies have been done for classifier comparison. Next slide. However, all these supervised learning methods require a large and accurately labeled data set. And this appears to be the primary bottleneck in widespread adoption of machine learning to analyze the results of static analysis tools. Getting these labels can be time consuming because you need an expert to go in and assess each of the alerts and then label it, whether or not it was a true positive or false positive based on some type of criteria, which also needs to be developed. This requires training. So a novice does not have the skills to do this. SEI has developed some tutorials for helping develop this, but these need to be done by expert auditors. And then finally, once we get a labeled set and we can build a satisfactory prediction algorithm classifier, this is not necessarily stable. So if we want to add new tools, if we want to upgrade the tools, if the outputs of the static analysis tools change, that would require a change in the data and then retraining the classifier. So the process would need to start all over again with auditors going back in and relabeling now a new set of data. Next slide. So what we propose is to use active learning to optimize or efficiently label alerts. And active learning is a machine learning paradigm where you start with a small set of labeled examples. You build a machine learning model. and then the active learning is used to select labels from an unlabeled set to be passed to an oracle. The oracle in this case is the auditor, and the oracle then labels them, passes them, adds them to the labeled set, and the machine learning algorithm is retrained. And this process iterates until a satisfactory predictive level, performance level is achieved. Next slide. So here we've developed this active learning for a static analysis. This is how we envision it, the workflow going, where we would run the static analysis tools on the source code. We would extract features from the source code and from the static analysis results that can be used for as data for a machine learning algorithm. We select an initial set for training set for labeling. We pass this to the auditor, who then labels it. We learn a binary classifier, and then we use active learning to select new alerts to pass to the auditor. Next slide. So in order to test this, we first developed a data set from the Juliet test suite. This is publicly available on NIST and is composed of both C and Java code. And these have common weakness enumeration alerts embedded in them that should be picked up by the static analysis tools. And here we have the labels that we or the features that we selected. Next slide. And we tested two standard active learning algorithms. One is the uncertainty algorithm, which is the uncertainty of the predicted label, and then query by committee. And we also, as a benchmark, just did random sampling to add to the labeled set to label by an auditor. And we also benchmark against, well, what happens if we build or do cross-validation on the entire 60,000 alert data set. And what our benchmark was around 0.93 and above, between 0.93 and 0.94. And what these results show is that we can get similar performance for using active learning with just a small fraction of the alerts labeled. So here on the x-axis, we have the number of queries. I think we start off with an initial labeled alert set of about 50 alerts, maybe a little bit more than that. And then at each query, we just add one more. And so what we see is that instead of having to label all 60,000 alerts in our data set, we can get away with just a fraction of just a couple of hundred and achieve similar performance if we are using active learning and smartly label the alerts. And with that, I'll turn it back over to Peter.
Okay, thank you, Stephen. Yeah, so our message is pretty simple in this project. There's a broad mandate within the department to use these tools, but there's a kind of productivity train wreck coming in terms of how do you use them and in what ways do you actually deal with the alerts that they produce. It's one thing to just run the tools, but then acting on the information that they provide engenders a very significant productivity problem. So we've attempted to address that problem in two distinct ways. One, by making use of our understanding of risk modeling that was embedded in CSRM and our mission-aware kind of cyber resilience framework. And the other by introducing some novel AI approaches and optimization framework, the CAP methodology and the active learning that Davis and Stephen spoke about. So we've made a start in addressing these productivity problems. We've done this work on our own and also in collaboration with Software Engineering Institute. And what we collectively, the researchers collectively need at this point are new partners who are kind of seeing this coming down the pike, who want to make use of static analysis tools, seeing it being an issue of scaling that's coming sooner or later. And we'd love to hear from you and work with you on this. So with that, we'll stop and take any questions. Thank you.
So Peter and team, thank you guys so much for the presentation. Regarding the research itself, one thing that I've noticed again and again and again throughout these is the integrity of the data. Seems to be something where the data itself is either mislabeled or there's something else. And what I like is that this project is kind of working towards trying to overcome that. Are there any other, like, because of the limitations that you have, are there any other data sets that you can think of that might actually help to be more representative?
Yeah, so it's a good question, James, and I'll see if the others want to take a crack at it as well. But let me just say, yeah, I didn't mention the limitations that we have, and one of the reasons for my call for for broader testing is that we've tested on ArduPilot, and we've trained our AI methods on an artificial data set. We'd really like to try things out on a real system. And of course, that brings a lot of attendant challenges, right? That we're a university, we can't easily work with a real system. So we'd be especially interested, to elaborate on what I was saying about partners. We'd be interested in having partners who could work with us, and maybe apply some of these methods that we have in the settings that we can't go into, of dealing with actual weapon systems or other kinds of systems and real DoD code bases. So we'd that's the kind of validation that we're seeking at this point. Again, it requires a real partnership. Does that answer your question, James?
No, it does, in that, like, just some of the limitations of being university and then working to try to
that's right.
a representative data set. I think that's like a well, I mean, that's why we kind of have these kinds of conferences and things like that, isn't it? So that we can kind of like show the research, right, and kind of bring it up.
Yeah, but then ultimately, to validate things, we want people to bring it inside a program and do some tests there in some kind of way.
So we actually got another question too, from Alan Moulton. You mentioned STPA at the beginning, but I didn't see that method used. Did I miss it? Or did you decide against the STPA to model feedback control?
No, yeah, it's a really good question. We kind of finessed right past it because it's a bit to explain, but yeah. So first, STPA is a just for everyone else's benefit. I think Alan already knows this, but STPA is a control-oriented way of thinking about loss and hazards. We use it in the context of mission aware and CSRM, our cyber resilience methodologies, and so what we did with ArduPilot, and Tim can give the details, but what we did do an STPA analysis, just didn't show the results. Is there anything you want to add to that, Tim?
No, I mean, yeah.
Okay.
I mean, part of it also was, even though ArduPilot's open source, we didn't have much expertise in ArduPilot itself.
Yeah.
And there really wasn't a mission we were applying it to, so that's why there's a bit of hand waving there.
Yeah, it's a good point. In all fairness, right? So that when we think about STPA, we think about that as being something that is really got to be done by the people that own the mission and the system, because they're the ones that can reflect on what losses mean and the way in which losses should be prioritized, which is an essential part of it. And that's hard to do with something, again, getting back to James's question earlier, it's hard to do with something like ArduPilot, which is an open source piece of software that's really not owned by anyone, and without a mission. So we had to play roles ourselves in that process that we wish other people would play. Again, getting to the need to, please come and partner with us if you have some software.
And that's the trick. Thank you. We're a little over time, but I really appreciate it. And I'd like to thank everybody else for attending as well. And I hope to see you all soon. Everybody, very good talking to you.
Thank you.